Let's go over some code for image manipulation in Python. This is a code notebook that uses a Python package called PIL. PIL is short for Python Imaging Library, and this is a free open source library that's pretty easy to use and enables you to do a lot of different things with images. So you can see these are some functions and methods that we use as part of this PIL package. Well, some of them are quite simple. For example, this one, open. Well, we can open an image when it's stored in a file on your computer or in a Google Drive. Loading the image. That's going to extract the pixel map from the image. Remember, we're talking about representing images as matrices or 2D arrays of numbers. Each number represents a pixel. So we call that matrix a pixel map, and load is going to give us the pixel map. Display doesn't give us the map, but it gives us the actual image that we can just sort of look at and see each of the colored pixels together. Size shows us the width and height of an image. GetPixel gives us individual values from the matrix that represents the image. So the values associated with one individual pixel in the image, you get that from GetPixel. You can save the image with save. You can convert the image between different image formats, like RGB to HSV. And finally, you can get individual channels from the image, like get all the red, all the green, or all the blue. And remember, those are representations of the color components of an image. So how much of each pixel is red, how much of each pixel is green, and how much of each pixel is blue. Those are the channels. And we'll go over what those look like. Let's start simply. Let's just load an image. So the first thing we're going to do is we're going to do what's called mounting our drive. And so we're going to have files stored on Google Drive, and we need to tell the notebook where those files are so that when we specify a file that we want to load, it knows where to look for those files. In this case, we're saying the drive that we want to mount, or the drive that we want to access that has the files we need, it's at this location, /content/drive. That's our Google Drive. So we're going to mount it. Now that the notebook knows where to look for files. Next, we can import some libraries. Remember, we talked about PIL. We're going to use this image module from PIL and matplotlib, a very standard plotting library. We can keep going. We specify the location of the image that we want to load. So this is a file that's stored on our Google Drive. And so this is the file path. And in order to open that image, well, it's very simple. We just use image.open and specify the path. And there are lots of things we can do with that. The first thing we can do is, remember, we can use this load method. With the load method, we can find the pixel map, or what we're calling the pixel matrix here. That's going to be a two-dimensional array of numbers, and each number represents something about the color or the intensity of every particular pixel. And if it's a color image, it's going to be a collection of 2D arrays, an R channel, a G channel, and a B channel. Each of those will be one particular array. That's what our pixel matrix or pixel map will be. Before we look at the pixel matrix, let's first just display the image. So the display function allows us to do that. You can see it's this nice color image we have here. Well, we can check the width and height of the image using this size attribute. You can see here that our image has a width of 320 pixels and a height of 229 pixels. Let's keep going. Let's accomplish conversion from RGB to grayscale. This is a color image. So for every pixel in this image, we know some information about it. We know how much red is in that pixel, how much green is in that pixel, and how much blue is in that pixel. So if we want to convert a color image to grayscale, there's actually a formula we can use where we just take the mean of all of those three things. The mean of the amount of red in the pixel, the amount of green in the pixel, and the amount of blue in the pixel. The mean of all those things, we could say that's like the amount of white in the pixel. And if it's a very high number, if the mean of those three numbers is very high, we have maybe a pixel that's white, close to white. And if it's very, very low, we have a pixel that's black or close to black. And so this is the formula we're going to use to do this conversion. And you can see here we have nested loops that accomplish the conversion for us. So I is going to be an index, and it's going to go through the whole range from 0 to the total width of the image. And that's because it's going to be like our x coordinate. So for every pixel, we want to know what's like the x coordinate of it, or where is it on this width. And we want to know the y coordinate of it, like where is it on this height. And that way we can know the location of every pixel. So we loop over this I variable and this j variable. I is meant to represent like our x coordinate. J is our y coordinate. It goes all the way from 0 to the total height of the image. And once we have I and j, we can get that individual pixel that's at location I, comma j, or in other words, this horizontal location and this vertical location. When we get that pixel, remember we're going to get 3 values since it's a color image. We're going to get how much red is in that pixel, which we call R, how much green is in it, and how much blue is in it. We call those G and B. And to convert to grayscale, we just use this formula that we introduced here, the mean or the average of all of these channel values. And finally, we're going to do this conversion where we say, instead of storing R, G, and B values, let's just store this grayscale value here. That will be our pixel matrix. And now, when we display our image, look at what happened. We accomplished conversion to grayscale just by having a nested loop and by applying this formula. So this works, and you can see we have a grayscale or black and white image here. And this is a totally fine thing to do. However, researchers have discovered that the human eye is kind of a surprising or maybe a strange thing. And instead of taking the raw average of these 3 numbers, we can do something like a weighted average. And it turns out that, actually the green values seem to be more important than the blue values. Maybe the red values have sort of a medium importance. But when we want to convert to grayscale, we use these weights to get a weighted average of the R, G, and B values. And you can see if we use the same function, the same nested loops, but with this weighted average instead of the raw average that we have up here, we accomplish the same thing. We do a conversion to grayscale, but potentially, according to researchers, this is something that's easier for the eye to see and understand and interpret when we look at it. So you can use either of these methods to convert to grayscale. Now, you may want to convert not from RGB to grayscale, but from RGB to HSV. These are different formats that we can store images in. And so here, we're going to show an example of doing this. And we start in the same way we started before. We specify the path of our image. We open our image. Here we're saying convert it to HSV and then just show it. And here it is. You can see it's the same image, but now we've converted it to HSV. And that's all it takes. Since there's a built-in method for it, we don't need to do the conversion manually on our own. What we can do is, if you want to understand HSV a little bit better, you can get each of the channels of HSV, get the H channel, the S channel, and the V channel, and you can look at what they seem to be representing. So you can see here, we have this H channel, this S channel, they're trying to display it as well as they can, and the V channel. And so HSV is a little bit harder to understand than RGB, but you can see that it's one way to represent an image. And these are what the individual channels look like. It's a little bit more intuitive when we visualize the channels of an RGB image. And here you can see we take the image and we do a conversion to RGB. And now we can get that particular channel, get the R channel, or in other words, the red channel. And we can plot it. And so you can see here, this is a plot of our image. And you can see every pixel on this image, image of the R channel, tells us how much red is in every particular pixel in our original image. So for example, this part of the bird here, you can see it's not very red. It's kind of just white here. And that seems to indicate that that's not really a red part of the bird. And then we can see here as well, we have the same thing with green. Some of the darker or richer green areas, those are maybe the greenish or more green parts of the bird. And then the parts that have less green, those are, maybe they're red, maybe they're blue, or maybe they're white parts of the bird. And then we do the same thing again for blue. By combining all of these things, or in other words, by plotting them all together or on top of each other, that's how we're able to represent a color image that has all the colors of the rainbow. But we're sort of splitting it out here to see them individually. So this concludes our notebook, where we were able to open and look at some images and do a little bit of manipulation and conversion as well. Happy learning.